which it was discussed in the class. Basically, it provides a simulation. So based on that, what will be the capture zone? If we put a well, so how much, what will be the capture zone for if we are putting 6 wells? This question is basically asking that. So it's asking our upstream the width for upstream of well as well as downstream. So both widths we have to provide. You might have seen this diagram.
No, sir, I haven't seen. What is this, sir?
Hmm. So basically, this area basically represents the this. This is basically a well. So if you have attended the week 3 lecture, basically there we discussed if we after completing the risk assessment, we came to discuss the remediation methods. Like one of the methods for remediation you can do is like if you wherever the contamination is for specifically for groundwater, so we can create a barrier type of thing around the contamination, and we can restrict that, or we can pump out the water which is contaminated. So in that concept, there was one method which is Chavandal. If my pronunciation would be wrong for this method. So this method basically gives us idea of if we have a contamination zone of like this, right? And we have water groundwater flow in this direction, right? In this direction. So basically, this method is to determine where should we construct the well so that we able to cover this complete area. Yeah. So do we need one well? Where should be located? At which location it should be? How many wells we need? So this method is used to determine that. So basically, here we determine two types of width. Like if I make a well here, so zone will be something like this, right? Something like this. So if I'm making a well here, so this diagram, if we see in this figure, this width is calculated. Okay, this width. This width is basically capsule zone width at well, like the location of well. What will be the width of the capture zone? This is capture zone. Okay, this is like a top view. So, and if we see a side view, a plane view, it will be something like this. This is the groundwater level. This is the ground level, and some or something like this will be the groundwater cone. If we are putting a well and extracting water from it, there will be a depression, right? So if we see it, if we see it from sort of top view, this will be the, uh, the representation where this represents the well, and this is the basically the zone of influence, the capture zone of this well. When we are pumping out water from this well, it will take water from almost this zone. So whatever contaminant present in this zone will be typically removed. So for in this question, what he's asking is like we have to tell two information. One is capture zone width at the well and capture zone width far upstream. So this is far upstream. This is the width capture zone width far upstream. These values we have to calculate. So these two values this question is asking, but this question is asking these two values for six wells. Here we only have one well. So if we put, for example, six wells, so this type of figure will be there. So what he question is asking this width as well as the upstream width. So you have to calculate these two values. So now you understand the question.
Yes, sir. Like in how to calculate?
Did you attend the lectures? Hmm?
No, sir.
अच्छा, कोई नहीं. Uh, Ramesh, Ramesh, Mr. Ramesh, Mr. Ramesh, am I audible to you? Hello, Kirthana Ramesh. So basically, if you attend the lecture, um, I think lecture 11 probably. So in that lecture, this table is given. So for if we have only one well, we have formula this. So for one well, it will be this width of capture zone width at well will be around zero point 0.5, zero point 0.5 Q by BU. If we have two wells, the value changes. Three wells. So for n wells, there is a formula given in this table. So from this you can calculate. So you can note down this formula or you can go through the lectures. So now you can try to solve this question. You have to do this for six wells. And here in formula n represents well, number of wells. This is the formula. Spacing, W width at well and at upstream. This is the flow direction. So this side will be the upstream. This will be the upstream, and this side will be the downstream. So upstream width we have to calculate. Add add the contaminant closer to well, the flow velocity will be high as we go far away from the well. The zone of radius of influence, like if we assume this is the distance at which this well has maximum distance at which this well has influence. So the attraction which contaminants will feel at this distance will be very low as compared to contaminant which is very near to well. So velocity of flow at near to well will be very high as compared to at far distance. Were you able to calculate? You can say the answer, or you can also type in the chat box, comment box. Did you did you get the answer?
It's sir maybe three.
Oh, that is correct. So we have formula of 0.5 into n is number of wells, 6 into q divided by. So this will be 3. Similarly for this it will be 6 q by b. That is the correct answer. Second question is, this is on the same concept. The groundwater flow rate through a certain area perpendicular to the direction of flow. So this question is saying that let's assume this is the figure. Let me take this figure. So this is basically that, like if we are seeing the well from the top. So this is well and this is the influence zone of the well. So if I draw up a planar view of this, uh, it should be something like this. This is the ground and this is something like this. And this will be a well. This will be a well. No? And flow direction, something like this. This will be the flow direction, right? In this diagram, in the flow direction, if we see this, we have to like invert this image, sort of, for this flow direction. But I made the gradient this. If you made the gradient in this fashion, it will match this diagram. Let's make that fashion. This is the ground. Okay. And this is the groundwater. This is the direction of flow because of the gradient. And here we have the well. So the question is asking that the groundwater flow rate through a certain area perpendicular to direction of flow. So if this is the direction of flow, there will be the area which is perpendicular to the direction of flow. It will be something like this area, right? So direction of flow in the absence of pumping. And this is the well. So we are pumping out water from this well. But the question is saying if we are not pumping out water from the well, if we are not pumping out water from the well, or if the absence of the pumping is twice the rate at which water is pumped out. So this is saying that this flow, this Q value is two times of, question is saying this Q value, the the flow of the groundwater uh, is two times of, this Q value is two times of, in the absence of, is twice the rate at which water is pumped, is two times of QP. So this is saying that if this rate is QP and this is Q, so this Q is two times of QP. This question is suggesting this statement. So what do you
Mm,
think?
true,
Like
true,
this? Huh?
true, true, na?
No, it's not true.
True.
It's not true.
Oh,
It's not true. The statement is wrong. Correct statement is QP equal to 2Q. The rate at which we are pumping out water must be two times of Q.
okay, 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 okay.
So we had a derivation. We also did a derivation of this. Mm. If we assume like discharge to be A into Q, and we take the, if we are seeing it from like above, so the width, like the width which we calculate from here, right? This width. So this width will be this, right? Right? This thing, this width. If we are seeing it from top, this width will be represented like this in this diagram, right? So if we are taking it as the width, and if we calculate, then Q A into V, which this derivation was done by sir only in the class. So Q into AV, and Q area is basically you can split it into B into W into velocity of what, right? So W we have calculated. W we know how to calculate. We have the formula. The formula. We can replace W as 0.5 Q du. Q is equals to B into 0.5 Q. Now this Q is QP. Here in this formula, Q is the discharge at which we are taking out water from the well. So in this problem, here we have to replace, we will replace it as QP because this Q is different. This Q is basically this flow rate, flow of groundwater. QP into divided by the W. So A and will cancel out. So your discharge basically be equal to zero point 0.5 times of QP, which can also be written as QP equal to 2 times of Q. This is the correct statement, but in question, it is given that Q is 2 times of Q. This statement is false.
Okay, sir. Okay.
This is the third question. Like, take some time and try to solve. So let me, like you have not done the class, so let me explain the question. Then you take time to solve it. The pump and
Okay,
treat
sir.
method of remediation of contaminated groundwater is mostly not suitable case. So the pump and treat method, like uh, there's a plume contaminant side. This is the plume contaminant, and we basically put n number of wells as per requirement, and we remove the water, take out the water, and then we treat it. Or after treatment, we can do either we can re-inject the water, or we can use that water for some other use. So this method of treatment of to handle the contaminated site. So this method has some limitations. So basically, what are those limitations? Basically, if this question is asking what are those limitations. So you have to find out those limitations on these options. It is asking where it is not like pump and treat method of remediation of contaminated groundwater is mostly not suitable. किस condition में suitable नहीं है. That specific situation we have to find out from these four options.
I think it's first homogeneous aquifer.
Homogeneous aquifer, what is the reasoning behind, like what is the thinking pattern behind your response?
I think it's
Homogeneous homogeneous aquifer होगा
combination
तो
of
पंप एंड ट्रीट आपको करना है जैसे if I'm pumping water from जैसे soils. Hello, Aarti, am I audible? Okay. So if this is the ground and this is the like this is the soil. So mostly this method is more suitable for unconfined aquifers, right? Not suitable for not suitable for confined aquifers. So we have soil here, right? And there's one contaminated zone, and I'm pumping out water. So what will be more suitable if this soil is like a single type of soil, or or if this soil, like if even this soil there is some clay layer in between, or or there is stratification in between, if there is a layer of clay in between or silty clay in between. So the more different types of soil we have, there will be like what will vary. Like clay is not, it's porous but it's not permeable, right?
yes,
So
sir.
it does not have interconnecting voids. So which will be more difficult if the soil is of single type, or there are multiple types of soil? So you think in that
If
way.
if multiple type of soil is present, then it's not able to pumpable water.
So it's like what will be the reasoning you will give? Like what will be the problem in if we design?
If we're trying to pump out same water at clay or any silty soil, if same silt or clay is present, then the type of pump used is more suitable. If hard hard soil is present, then it's not able to pump.
So if we using a silty clay or sandy clay, so the permeability will be on the lower side. So basically the time at the end, the time required for the performing the treatment will be very high, which won't be feasible. We have to design for different types of soil, different types of K values, right? So if we have highly heterogeneous aquifer, it will be very difficult.
Okay, sir.
Rajesh, or am I audible? Mr. Rajesh,
Yes, sir.
have you attended the week 3 lecture?
Yes, sir. Partially.
Okay. So we have done 3 questions till now. So by once we will do all the questions, and then at the end we will revisit these 3 questions. Okay. So this is the next question. You take some time to read and do the problem, and at the end of that we will do it together. Am I audible to you? Are you able to see the presentation?
Yes, sir.
So this is the like you have you done the week 3 lectures?
No, sir, not yet.
Okay. So for now will proceed with the questions. You read the question and try to solve it. If you face some problem, we will discuss the problem. And I have already discussed 3 questions, so we will do it at the end of the lectures, right? We will redo it though.
Yes, sir.
We will discuss again. So this is the first question. Try to solve it. Like try to solve it. I will discuss the concept also. Just give it some time. So the question is asking basically what is the what is the cause of tailing observed while pumping out contaminated groundwater. So who have attended the lectures might have understood the term tailing there. There was a graph discussed in the lectures where something like this, where you have pumping duration and concentration of contaminant. So as like the time and relative concentration. So with the time when you are pumping out water, so let me discuss from the start. So in week 3, basically, we discussed different methods to remediate contaminated sites. Before that, we were discussing risk assessment, how to calculate what how much risk that particular contaminated site pose. If the site is posing a significant risk, we will think of remediating the contaminants, right? So the first method, one of the method is pump and treat. So if there is this is the contaminant source and it has started spreading, and this is the region where, so this is we are discussing for groundwater specifically. So week three was specific to groundwater. So in groundwater, if certain contamination source has spread in groundwater in this particular zone, and we have groundwater flow direction like this. So we want to remediate, we want to stop it. So that there is to, like, initially we can think that we might build a barrier sort of thing so that this contaminated region, this contaminated water does not contaminate the other aquifers, or does not contaminate the, like, complete groundwater present, right? So this may be one of the way. Other way is we might pump out this water. We make a bore well in this region and we pump out the water. So this well, like, if we are scientifically design the location, we can design the location of well, how many wells we require. So though all these things are in lecture three, week three lectures. Okay. So and how we design those wells is given in a particular method is there. This method. This approach is used to basically determine what will be the spacing of wells, what is the zone of influence for each well. So based on those concepts, here this particular question is asking that, like, if we are running this tube well for like 1 year, so during this time period, there will be there will be some reduction in the concentration with time, right? There will be reduction in concentration with time. And if we stop these tube well, this pumping out of water of contaminated zone, after some time there will be again increase in the concentration. So this is the tailing effect. So the question is asking, like, uh, why is what is the cause of tailing observed while pumping out contaminate from groundwater? So what is the reason for this? Like, if I build a well here, we can see in this diagram. So I'm building a well here. This is the well. This is the influence zone. Basically, this well can influence or capture contaminant in this zone, up to this zone. So the major reason for the tailing effect is, like, near to the well, the velocity of the contaminant, the flow near the well is very high because the suction force experienced by the particles near is high. On the contrary to that, the boundary of the capture zone does not influence that much of attraction toward the well which we have drawn, right? So here the velocity will be low towards the well of the contaminated particle. So because of that reason, the particles which are nearer, or the contaminants which are near to the well, will get removed quickly, right?
Yes, sir. More quickly.
Yeah, because they are experiencing more force of attraction, right? Because the well is near to them, and it is uh, taking water from the surrounding. So the particle near to the well are experiencing more force towards the well, so they get removed quickly as compared to particle which are near the boundary. So they take a lot of time to get removed. So because of that, there is a tailing effect. So if you understood what I just said, you try to answer the question.
I think it's first.
First is correct. Do other people have any doubt? If you don't understand something, you can ask me in between also. This is the next problem. In which of the following cases may we observe a rebound in contaminant concentration of groundwater? So like what is this question is trying to ask is like if this is the ground level and this is the cone of groundwater, this is the bore well which we draw, and we are taking out water at let us assume at QP. So what this question is asking that what actually happens is we are drawing water. When we are drawing water, like if we draw for T amount of time, so there will be some concentration, the contaminant coming out, but the contaminant concentration of contaminant during that T time will reduce. But if we stop the operation for some time and and after some time we again start the operation, again start drawing water, there will be some concentration again. Like for example, there is some Q concentration which is coming for T amount of time, right? This Q T, and with time it happens that that concentration start reducing, and after and for some time if we stop the operation, then again there will be some Q2 concentration in the water, and then we again run it for T2 time. There will be reduction in concentration. Then we again stop the operation, and after some time we again start the operation. There will be some Q3 concentration. So we are running the our tube well for removing the contaminant, and we are achieving a low. We are able to remove some contaminant which is present in the water. But if we run the tube well after some after a break of like some after a break of some months or years, whatever it may be, there will be some contaminant or concentration of contaminant of concern will reappear in the water. So what is the reason for that reappearance, that contaminant? So this question is asking basically that, like once we run an well for 1 year, we were able to remove a significant amount of contaminant, but again that contaminant reappeared. So what could be the possible reasons for those reappearance? So we have these four options, like presence of uh, DNAPL or LNAPL. So DNAPL are dense, non-aqueous phase liquid, dense non-aqueous phase liquid, and light non-aqueous phase liquid. So if these two types of liquids are present as contaminant or as an absorbent of contaminant, then there will be a reappearance or rebound in contaminant concentration of groundwater. Or second option is there's presence of stratification condition. Stratification, you are like if you have different layers of soil and each layer have different properties. Then next question is homogeneous condition. You don't have stratification. You have single soil with media, but you have high organic content in the soil. These are the three reasons which are given. So out of these three reasons, which in which conditions there will be rebound in contaminant concentration? This is the question I'm trying to ask. So you try to answer that, like which condition is most probable.
That is maybe stratification.
The person who attended the lectures, Rajesh, did you able to reach till this part? So basically, these uh, basically if we study, there are basically three mechanisms. The primary is if the contaminant which is present in groundwater is can get dissolved in the groundwater. So if it is aqueous, right, the contaminant get dissolved in the groundwater, then this normal pumping is sufficient, right? Like if this is the ground and these are soil particles, so where the water, like these are pore spaces, right? So water gets stored in the pore spaces, and if the contaminant is like dissolvable in water, then those contaminant will also be present in this pores, right? With the water which is present in these pores. So first condition is
Yes, sir.
contaminant is if a contaminant can get dissolved in the water, then there is no issue. If we remove water, the contaminant will come out. But
Yes, sir.
in second situation, the second case is if the contaminant is aqueous as well as it is present in soil. Present in soil means it can get absorbed on the soil particle. So if the contaminant is also present in water, but it is also present, it also get absorbed on soil particles. So if this type of substance, if we pump out water, do we able to get the all the contaminant present in ground? If we
Yes,
pump
sir.
out,
Because soil has absorbed.
huh?
No, sir. We can't able to. No, sir.
Yeah,
We are not able to.
we won't be able to, है ना? If if
Yes,
the contamination is here, soil particle, if this is a soil particle and contaminant, we have this contaminant absorbed over this soil particle. Now we have removed water. This is the water level now, but we can't get this
yes, sir.
contaminant, right? So once we stop
Yes, sir.
QP, this water level get restored, right?
Yes, sir.
So now the water which get restored, this contaminant will come out in water, right?
Yes, sir.
Because this you must have heard of octanol water ratio.
Yes, sir. Yes, sir.
No. So based on that, like it basically gives us information if a particular compound how much soluble it is in water. Say if I dissolve a compound in octanol and if I dissolve a compound in water, what is the ratio? So if this ratio, if this value is very low, that means the solubility in water is very high, right?
Yes, sir.
If the KOW value is high, that means the solubility of that compound in water is very low. So basically, so at at time zero, when we have started, we have just started the pumping. This contaminant, the solubility is very low because if a certain compound has very low solubility, it will get absorbed on the soil particle because of its nature. Uh, Hydrophobic, hydrophilic nature, you might have heard of. If it is hydrophobic, it will try to run away from water. So some of the particle are there in water, So there will be a sort of equilibrium between the interface of the particle getting absorbed on soil particle as well as particle in dissolved form. So once you remove the water, so these particles also get removed. The new water which comes resurfaces in this region won't have these particles. So there must be some equilibrium between the particle absorbed on soil and water interface, right? So some of the particle will move into water. So now again, so because of that, there will be some contaminant again in groundwater. So now we again pump out the water. So those
Yes, sir.
contaminant
Yes, sir.
which, so because this is the reason there will be again and again some contamination in groundwater slowly because of the nature
Again,
of
come
contaminant.
into the water. Yes, sir.
Yes,
Yes, sir.
it is not aqueous, completely aqueous. So this was the second case, and there is third case when you have aqueous as well as adsorption, as well as you have certain compounds called NaPl. The NaPl is non-aqueous phase liquid, non-aqueous phase liquid. So these are basically like if I call this soil this contaminant, this is the contaminant. NaPl will exist as a like a ball sort of thing. Okay, here. So it won't get dissolved in the water. It won't get adsorbed on the soil particle. It will like it will be present independently in the soil. So this is sort of particle which with time with time it will get dissolved or it might not get dissolved or it may contain some contaminant because if some contaminant which is not soluble in water it might move to this NaPl liquid, non-aqueous phase liquid. So these are the three situations. So NaPl can be divided into two further two like dense non-aqueous phase liquid or light non-aqueous phase liquid. So how do we distinguish these two is like if this is the groundwater level and this is our ground level. If we have some contamination of like gasoline here in petrol pumps, where the petrol and diesel are stored underground, right? So if we have some leakage from there into the soil and that gasoline goes into water, so initially that gasoline, the density is higher or lower than water.
Lower than water.
So it will get some of it might get dissolved, but it won't sink to the bottom, right? It will mostly stay on the top.
Yes, sir. Top.
Yeah. So this type of liquids are basically LNAPL.
Okay.
On the other hand, if we have contaminant like PCE, which have high density as compared to water, so in this case, what will happen? This compound will sink to the bottom. Like if we have
Yes, sir. On
contamination
bottom
here
part. Yes, sir.
and it will sink to the bottom,
Yes.
and or some of it might get dissolved also. So this is the example of DNAPL. So if I'm pumping water from here, let's assume, you know, I'm pumping out water, whatever dissolved concentration present, I remove. Uh, will all have I removed all the contamination? If I for some
No,
time I
no, sir.
remove,
No, sir. Because of the
no.
settled down particles are not able to remove.
Yeah. Again, water will replace the removed water, and some of this PC will again get dissolved in the water, and there will be a rebound in the concentration of PC. Similar, same thing will go for LNAPL, right? So from this, we can note that presence of DNAPL or LNAPL will support the rebounding of contaminant concentration in groundwater. This option is correct. So our second option is stratification condition. If we have different layers of soil, so different layers of soil means different permeability might be there. So if a well is there,
Yes, sir.
so if permeability is different, that means contaminant present in two different layers won't reach the well at the same time,
Well, yes, sir.
right?
Yes, sir. Yes.
So there will
Yes,
be
sir.
variation. There will be a rebound in contaminant concentration of groundwater because of stratification also. Stratification is
Yes,
also
sir.
correct. Then again, homogeneous condition. So this will be because of absorption. This same concept we studied in uh, case two,
Okay, okay.
dissolved
Means
and
the
absorbed
soil
condition, right?
absorb the organic
Yeah,
content.
yeah. So all three
Okay,
options,
means the option 4 is correct.
all
Option
three are correct.
A,
So
B, and
answer
C
will
are
be
correct.
four.
Yes, sir. Okay, sir.
Okay. This concept you can refer in lecture 14, slide 9 also. Search slide. I have
Okay.
explained almost, but uh, if you want to further study, you can also refer slide 9, lecture 14. This is the next question. This is basically a numerical. So try to solve the numerical if you have covered it in the lecture. Otherwise, we will do it together. Take some time, like whatever parameters are given, whatever information you can extract.
So there is a any one formula for calculating the KP.
What? पार्टीशन कोफिशिएंट का फॉर्मूला
Formula, sir. Yes,
केपी
sir.
का फॉर्मूला पार्टीशन कोफिशिएंट का फॉर्मूला होता है के ओ सी एफ ओ सी तो इसमें के ओ सी होता है सॉइल वाटर पार्टीशन कोफिशिएंट और एफ ओ सी होता है अपना ऑर्गेनिक मैटर फ्रैक्शन ऑफ ऑर्गेनिक कार्बन try to solve this. I will ask the answer. Take 3 minutes.
Yes, sir.
Did you get the Kp value?
No, sir.
So if we directly solve this problem, like because most of you have not attended the done the lecture 3, directly using this formula won't much help much. So let me like explain the this concept first. So it's like once we have one like I have little bit explained the what like in pumping and treatment what we do. So let me explain the mathematical part of the if like if you're going to design it, how you will approach sort of thing. So if you same thing is also explained in lectures also. So you must have heard of mass balance equation.
No, sir.
So if I want to like if this is the area, this is like assume this is a pond and there is some contaminant here. No. So if I want to calculate what is the concentration of that contaminant or how much contaminant is accumulated at a certain time, so how I will calculate? There will a stream of water which is coming into this pond and there is stream of water which is going out of this pond, right? Or there and there is already some concentration of C. So how I will calculate that at particular time, what is the concentration of particular contaminant or how much water is present in this? So I will basically do that how much is the intake minus how much is going out, and I will also add what was already there, right?
Yes, sir.
This will basically give me a sort of value or accumulated value of contaminant or how much, let's assume how much water is there, that value. So similar sort of thing is done here. Like if I want to calculate how much contaminant I have removed and how much contaminant is left in the groundwater, so I will calculate it through mass balance like accumulation. How much contaminant is still there that will be calculated through how much we have put in, like how much we have put inside the contaminant or how much we have removed plus how much contaminant is formed inside. So mostly if we are dealing with groundwater, if we are not dealing with microbes, so they won't be sort of coming the contaminant. If we are assuming a certain heavy metal, it won't be forming inside the groundwater, right? So, and how much is lost? So, if I take this as dm by dt, variation of that contaminant with respect to time, we are not inputting any contaminant, right? So, input will be zero. We are trying to remediate the site. So, we are taking out the contaminant. You know? So, when we are pulling out the contaminant, we are pulling out it at flow rate and it has C concentration, C milligrams per liter of contaminant. So if I want to calculate the value, how if I want to calculate how much mass is taken out per unit time, this dm by dt is basically what? Unit of mass divided by time. So if I take it kg per second, for example, so this mass per unit time will how we will get. we have to multiply Q and C, right? Q is meter cube per second or liter per second, and C is kg or milligram, whatever you want to take, milligram per liter or kg per liter. So liter will cancel out kg per second. So we will have Q into C. Q into C will give us the mass per unit time, how much mass is extracted per unit time, which is this out. We are not putting any contaminant, because our aim is for remediation. No contaminant is forming inside the system, and we did not lose. We are assuming that we are not losing any contaminant. Whatever the influence zone is where contamination happens, we are able to cover all of the complete zone, and that the tube wells what we have made and remediation what we are doing, we are able to remove, we are able to cover all the contaminant present in the zone. So we are assuming that, so we are not losing anything. So this is also zero. So if we integrate it from 0 to t, we will get m at t time minus m at t equal to 0 equal to minus qc. So this is mass of the contaminant at t time. Like if we are pumping out, like if we are pumping out from last 2 months. So at the end of those 2 months, what is the mass left? And mt at t equal to 0 means when we just started pumping, what is the mass of the contaminant is equal to minus the qct. Q is the flow and C the concentration, T is time. So if I want to calculate the time for remediation, right? Like how much time it will take to remove this complete M mass of contaminant which is present in M T equal to 0. How much time it will take this M to remove. If I want to calculate, I can calculate it as T, and if I am talking about remediation, what will be the value of MT, mass of contaminant at time T? What value of MT I can assume if I'm taking it as complete remediation? Mass of contaminant at time T. This time I'm calculating for remediation, like complete removal. What should be the value of MT? It will be 0, because I'm assuming that at T time I'm doing complete remediation, so there is no mass of particular contaminant left in groundwater. So MT will be 0, right? So from this, if I calculate, TR value will be mass of contaminant at time t equal to 0 divided by QC. This is a simple equation by which we can actually calculate the time, how much time is required to remove the particular contaminant from groundwater. And Q is basically QP, discharge rate. C is the concentration of contaminant initial. So once we know this, uh, now for calculating the TR, we need some information, like we need to know MT. We need to know MT value, right? If we don't know MT value, how we calculate TR? So how do we calculate empty value? So empty is basically, what is empty? Empty equal to zero. Or we will call, from now we will call it m naught. Can anyone tell what is m naught or empty equal to zero? M is basically mass. Empty is basically mass of particular contaminant at t equal to zero, means as the original concentration. We haven't done any remediation yet. At that time, what was the concentration of any contaminant in groundwater? So the total mass of that contaminant. So to calculate that mass, how can we first, like, this value calculation value will vary based on which case we take. If the contaminant is completely aqueous, means it can dissolve in water. So in that case, there will be a comparatively simpler calculation. So let's assume we are doing it for case one, when the contaminant is dissolved in water. So when something is dissolved in water, in groundwater, so groundwater basically is present in pores. So if we know the volume of pores, we know the volume of water, right? So for knowing the volume of pores, what should we do? Like if I know the volume of the complete soil area, if I know the volume of the soil in which the contamination is there, can I calculate the volume of pore from that? So
Yes, sir.
how would I do it? If I know the
The
value of
calculation of
porosity of soil,
total area.
so if I multiply porosity into volume of the whole soil, let's assume we are taking this square as the volume of particular this is the region where we need to do treatment, and this is the volume of soil, and we need to calculate the volume of pores in this cube. So if I multiply the volume of this cube into the porosity, will I get the volume of pores? So do anyone know the formula for porosity? Formula will be Vp by V, right? Volume of pores divided by total volume, right? So if we know the porosity, we can calculate the volume of pores. Once we know the volume of pores, it will be equal to volume of water, because water is stored in pores only. So if we
Yes,
know
sir.
the volume of water, and if we know the concentration of contaminant in water, right? If we know the concentration, and if we multiply it with volume, because concentration will be milligrams per liter, and volume will be in liter. So liter will cancel out, and we will get mg. We will get the mass, basically mass of contaminant which is present, right?
Yes, sir.
So m naught value we can calculate directly as n. N is porosity into volume, total volume of the region, into concentration, C naught, initial concentration. So this will give us the m naught. So if we replace this here, if we replace if we replace m naught here, what will the formula of PR be? N V C naught divided by QC. C C C cancel out. Porosity in volume divided by discharge will give us how much time we need to remove the contaminant. How, like, basically how much time we have to run the tube well for removing the contaminant, complete contaminant, right? So similarly, similar formula can also be derived for case two, where the contaminant is aqueous as well as adsorbed. So let's insert new slide. So in that case, uh, case two, where aqueous as well as adsorbed on soil. So in this case, the MT value will be the total M naught value. M naught value will be the first component which is present in aqueous phase. The calculation will be same as this, right? So it will be NCV only for aqueous phase. It will be NCV only. But when the part which is adsorbed in the soil, that we have to calculate. So that, like, if we analyze a sample, we can get Q value. Q value basically give us how many milligrams of particular contaminant is present in 1 kg of soil. This value we can find out. So it will come here Q, but we want mass. So we also need to calculate the how much soil we have. The volume, which this volume, no, in this volume how much soil is there. We need to calculate that. Then only we will get milligram or kg, how much kg of contaminant is present which is absorbed on the soil, right? Because so for that, what we have to do, we need to calculate how much soil is there. So how can we calculate? If we know the density, bulk density of the soil, so it will be density. So density का formula क्या होता है? Kg mass divided by volume, kg per liter. If we know the value, kg per liter or meter cube, and if we multiply it with volume of soil, so we will get what is the weight of the soil, and that weight of the soil, if we multiply it with Q, we will get how much contaminant is present. So Q into V into rho. This will give us how much contaminant is adsorbed on the soil, right? Did you get this calculation? Jadab, did you get this calculation? Someone listening to? Am I audible? Is this understood?
Yes,
Is this part understood, or do you want me to explain again?
sir, explain again.
समझ में आ गया क्या? जैसे soil, if we have soil particles, there will be contaminant which is absorbed on the soil particles, right? So we can calculate how much uh, particle are absorbed on the soil in terms of this unit, like how much milligrams of contaminant is present on the soil. So we can use a formula called Q equal to Kp into C naught. C naught is basically concentration which is present in aqueous groundwater, what is the concentration of contaminant in groundwater in aqueous form, and Kp is partition coefficient. So based on that interface only, there will be like what is the concentration in water. So some of the contaminant get absorbed on the soil, or it is in reverse direction. Majorly, the contaminant is absorbed on soil particles, and when water comes in contact with soil particles, some of the contaminant comes into groundwater. So it happens on in the basis of this formula, right? So we can calculate Q value from here, and once we have Q value, if we know how much contaminant is there in 1 kg of soil, we can calculate uh, the mass for the V volume of soil because we know the bulk density of the soil. So we will get this formula.
Yes, sir. Yes,
So if
yes,
we
sir.
replace this Q value, yes, Jada. If we replace now, we can replace it C naught plus Q. We can replace with Kp Qv. This is the M naught, and Kp value. The formula I've already told. KOC FOC. So now in normally in case one, when the medium is when the contaminant is completely aqueous, there won't be any delay because as you remove the water, the contaminant will come out. But if the contaminant is adsorbed in one iteration, the complete contaminant won't come out, right? You have to pump water initially. If like you are pumping water for 1 month, some contaminant will come out which is in dissolved form, and then you leave it for some time. Then the contaminant which is adsorbed will again come get deabsorbed and desorbed and will come into water, and then again you pump the water out. You will remove some of the contaminant, then again you leave it for some time. So you need to do multiple number of iterations, right? So there will be time difference if the contaminant is only aqueous as compared to if the contaminant is aqueous as well as adsorbed. So that time difference or that time extra time which is required, which we can calculate it in the form of retardation, basically retardation factor. How much, because of the adsorption of the contaminant on soil, there is retardation in the removal of the contaminant. So that retardation factor can be calculated through a formula called m naught divided by mass mass of contaminant, mass of mass of contaminant in water, right? This is a formula. So if we divide this m naught with mass of contaminant in water, mass of contaminant in water will be n v c naught. So R value will be, this will cancel out. So it will be 1 plus Kp divided by velocity. This is with the R formula for case 2. So once we now we understand the concept, you try to do this numerical. We have all the information to solve this numerical. This is the TC is a contaminant name. This is this is the length, breadth, and depth of the zone. So how we will use this information to calculate volume? Organic fraction, organic matter fraction is given. This is FOC. Soil water partition coefficient. This is KOC. This is porosity. Bulk density is rho v, and Kp value is asked. There's an additional question, question 7, which is dependent on this same data. So first calculate Kp, then we will move forward. Next seventh question is will ask for R, retardation factor. Try to solve. Did you get the Kp value? Kp is equals to KOC, which is 150 liter per kg into FOC will be 2%, which will be 0.02. What will be the Kp value? Can someone solve? Can someone tell the Kp value? Kp value will be 3 liters per kg. Am I audible to guys? You're not responding. If you have some doubt, you can ask at any point. This is the next question, which is dependent on the same data. The value of retardation factor, R value we have to calculate for the same question. R value formula we need, so this is the formula. You can use this formula. Try to calculate. Let me write it here. We have to calculate R. So R will be 1 plus Kp rho V divided by porosity. Calculate R value. Calculate R value. Tell me the answer, please. You just have to put the values in formula and calculate R. So R will be equal to 1 plus Kp. Kp value we have calculated 3. Let me do it here. R equal to 1 plus Kp value is 3 liters per kg into bulk density, which is 1.65 kg per liter divided by porosity, which is zero point 0.4. What will be the R value? 1 plus, solve this value. 1.3 into 1.65. It will be 12.375. So the R value will be approximately 13.4. So if we try to understand this retardation factor, like 1 plus 12.375. So because this one, if we take this one as 1 year, so because of the adsorption of this TCE, because this part is adsorption part, right? Because of adsorption, there will be 12 times more time required for the removal because of that adsorption. If it was only dissolved form, we will take only 1 year, but because of the adsorption, now it will take 12 more years, means total of 13 years. So you can, from this you can also judge the implication of if the contaminant is adsorbed, why it might be not feasible if the material is adsorbed, because it increases the time required for treatment by like many folds. So if in this question, if we have had a contaminant which is a non-aqueous phase liquid, it will be in lakhs of years. So that is not feasible, right? So so from this you can get an idea like what type of contaminant and what type of nature it has. If it is adsorbed or aqueous, so should we go for the pumping and treatment method, whether it is feasible or not? Like, R value we're getting here 13.4. This is the last question. I think you can answer this question. This is an easy question. Consider four different situations in which groundwater is contaminated by different solvent as follows. For different solvents, K octanol water ratio is given, KW values. So we just discussed whether how K or W value impact the solubility, how it represents. Basically we can uh, like determine whether the contaminant is soluble and how much solubility is have in, if it is whether it is in lower end or higher end of solubility in water. So we KOW value is given for four different contaminants. So you have to arrange them. How you have to arrange them? The all components are treated by pumping, and if we are pumping, we are using pump and treat method. So select the case in which rebound and tailing will be most probable, right, to least probable. So contaminant which will have more tailing, that means we have to perform the pumping again and again. So and to a contaminant where you have to perform pumping minimal number of times. So in that order you have to arrange. So how you will do it? You can determine that well that information from KOW value. How much a particular contaminant is soluble in water. More the solubility, lesser will be the tailing, right? Lesser number of pumping we have to do. More the solubility. So how solubility is connected to KOW value. Lower the KOW value, higher the solubility. So based on this information, you try to KOW value. If KOW value is low, implies solubility is high. Solubility high is implies low tailing. Cyclohexanol KOW value is 1.23, but trimethylamine KOW value is 0.27. Benzyl alcohol KOW value is 1.05, and ethanoic acid KOW value is 0.6. So lower the KOW value, higher the solubility. So if for solubility, if we arrange, so more soluble will be methylamine. Methylamine will have highest solubility. Basically, two will have two will have highest solubility. Then will be 4 ethanoic acid. Then it will be 3. Then it will be 1. Cyclohexanol will have the lowest solubility. So higher the solubility, lower will be the tailing, and we have to give it the most probable to least probable. So most probable tailing will happen in this one. For tailing, sequence should be 1, 3, 4, and 2. Which option matches it? 1, 3, 4. C option is correct. These are the problems for today.